Hello students, welcome to the new video of digital electronics. In the previous video, we have already seen what is NOT gate, AND gate and OR gates, out of which the very interesting one is a NOT gate, which is going to perform the operation of complement or negation. This is the symbol of NOT gate, which has got one input and one output. The basic property of NOT gate is if you provide A as the input, then output will be A complement, and it is denoted in this fashion, where the bar above that A indicates that the whatever input provided at the NOT gate will be complemented at the output. So this is the terminology that we have studied in the previous few videos. Now what if there is a situation in which there will be two inputs or two boolean variables are present, like A, B, C, or more than two? Then in such cases, if that particular operation is complemented or if it is negated, that is, if you connect NOT gate at the output of these type of circuits, then what to do? What will be the terminologies and what will be the outputs for different variable and different situations? Now, to understand these concepts, there is a theorem which is described by the scientist De Morgan's, and that theorem is about De Morgan's theorem, right? So now we are going to study in this video the De Morgan's laws. What are those laws? Those laws are related to the negations, and these two laws describes the situations when there is a complement of and or operations. Okay, so let us see the two laws. First of all, let us see first law. The first theorem or first law says that for any boolean variables A and B, here it is written down as, and how to read that, A dot B, and upper there is a bar, so it is read as complement of A and B, right? So dot represents a logical and, right? So therefore logical multiplication or logical dot represents a and operation. So complement of A dot B is logically equivalent to complement of A or complement of B, right? This plus sign is describing OR operation between the two variables, right? Here the variables are not only A, they are complemented. So therefore, again I'll read this statement: complement of A and B is equal to complement of A or complement of B. This is the statement of De Morgan's first law, or we called it as a De Morgan's theorems. This is the first theorem which is describing the complement of AND operation. So if there is an AND operation between the two variables of two Boolean variables, then in the outputs case, or it will be substituted, that is dot is substituted, see, by plus sign. That means OR is AND is complemented as OR, and individual Boolean variables are complemented at the output side. So let us see how to prove this De Morgan's theorem. It has got LHS side, and the LHS side is actually describing NAND gate, right? See, because A dot B is complemented, so it's a complement of A and B. So whenever you are going to say complement of A and B, this means that is not AND, so therefore it is NAND gate. So the situation of LHS is described by the circuit realization like this, in which there will be two inputs A and B. These two inputs will be given to the NAND gate, and the output of NAND gate will be nothing but LHS side that we wanted, that is complement of A and B. Whereas on RHS side, the circuit diagram which will be present is called as bubbled OR gate. You have already studied OR gate. This is bubbled OR gate. Now what is the bubbled OR gate? As I have already told you, the small circle which is written after this AND gate, right? There's a diagram of right? This diagram. In this diagram, see, this is a small circle present after AND gate. This small circle is nothing but presence of NOT gate, which is negation. So here in the case of bubbled OR gate, the presence of NOT gate will be present before the inputs. That is, whenever the gate is present, before that there will be bubble, that is there will be NOT gate. So let us see the diagram in detail and then we'll see the description. See, this is the diagram. Here you can see that this is the OR gate, right? This is OR gate which has been described previously. This OR gate has got two inputs. The inputs are actually A and B, but these two inputs are not directly going to the OR gate. This input A will pass through NOT gate, right? This will pass through a NOT gate. So therefore, after passing through NOT gate, it is going to create the complement of A, right? NOT gate's output will be what your input will be complemented. So therefore, the output of, right, the output of this NOT gate will be, in this case, this, right, A complement. Similarly, this B input will pass through this NOT gate. The output of this will be B complement. Now these two are acting as an input for this OR gate, right? This is an OR gate. Now the OR gate's terminology is that whatever input will be added logically. So therefore the inputs A complement and B complement will be added together, right? So therefore this diagram is called as bubbled OR gate, or this is a representation of bubbled OR gate, in which LHS side complement of A and B is complemented as complement of A or complement of B, and the diagram of bubbled OR gate is like this. Now here you will realize that these two bubbles or these small circles which are present now at the input side of OR gate, so therefore they are called as bubbled OR gate, and this bubble represents actually these two NOT gates. So one bubble at the input is nothing but this NOT gate present at the input. So this describes to you that, or you will understand that whenever you will find this type of diagram or this type of representation, you must realize that the input is complemented and then given to the next diagram or next gate. So therefore this is bubbled OR gate representation. Remember students, this is bubbled OR gate. So this is the De Morgan's theorem's circuit diagram representation. This is how you can realize the given logical expression converted into circuit diagram. So logical expression is complement of A dot B is equal to complement of A plus complement of B. The truth table wise verification can be done like this. In the truth tables case, here you need to identify how many different Boolean variables are present in the given Boolean expression. This is Boolean expression which is written down here. Here in the Boolean expression you realize that there are total two variables A and B. So therefore in the column I have written down one variable as A, another column one variable as B. And since there are only two variables and the impossible states of these two variables will be obviously, right, 1 or 0. So that means there will be two states, right? Now since there are two states, so all possible combinations will be 2 power states. That is 2 power states, and number of states, possible states is 2 power 2, therefore 4. This 2 is indicating number of inputs and they are A and B only, right? So therefore if there are A and B inputs, that is 2 inputs, and possible outcomes will be 1 or 0 of A and B, then the possible combinations will be 4. That we have already seen in the truth tables of every AND gate, OR gates, and NOR gates, XOR gate. Everywhere you realize that there will be only 4 possible combinations. So here also 4 possible combinations can be created. So here written down A and B. I have specifically left it blank because now I can show you that how to enter these possible combinations. Here the combinations I am supposed to write down are 0 0 0 1 1 0 and 1 1. But there is a trick to write it down. Here there are two inputs that has to be written down for different combinations. Then what I need to do is that I have to write down two consecutive 0 for first and then two consecutive ones, right? Similarly here two instead of two consecutives, here you need to write down one that is consecutive alternate ones and zeros. First I am writing down 0 and then 1, then 0 and then 1. This will be creating four unique input combinations: 0 0 0 1 1 0 and 1 1. Now let us see. Now let us go towards the LHS. Now in the LHS we want to find A dot B ka complement. So therefore first finding A dot B, and A dot B is nothing but AND gates operation, and AND gates operation says that if all inputs are high then only output is high. So here final combination, all inputs are high, then only output will be high. All other operations, all other inputs will be 0. So therefore this will be, see, this will be 0, right? Now we don't want to find A dot B, we want to find LHS as a dot B ka complement. So therefore the complement, that means 0 will be complemented to 1. So the output of this will be 1, this will be 1, this will be 1, and only this will be 0. Why? Because 1 ka complement will be 0. So this clears your LHS side, right? A dot B complement of A dot B. Now let us focus towards RHS, and in the RHS we want to find complement of A plus complement of B. So therefore we want to find first A complement. A is written down here in this column. It is A, which is describing you as 0 0 1 1. So I am writing down its complement will be obviously then 1 1, right? 0 and 0. And B complement, the B's inputs are 0 1 0 1. So therefore it will be complemented as 1 0, right? 1 0. Now the RHS. Now in the RHS case, here the written down as complement of A or complement of B. The OR operation says that if any input is high, the output is high. If any one input is, right, high, that is 1, then output is 1. So therefore here the two inputs are 1 1, that means at least one input is present as a 1. So therefore output will be 1. Here 1 0, that means one input is present, so here it will be 1. Here it will be 1. And here both inputs are 0, and when both inputs of OR gate are 0, then output will be 0. And therefore here realize that LHS ka column and RHS ka column both are same. Therefore you can say that, or you can verify by truth table also, the De Morgan's theorem, that is first theorem, is proved. Theorem is, again I am quoting you, complement of AND is equal to complement of individual inputs of OR. There will be operation as OR. So complement of A dot B is equal to complement of A plus complement of B, right? So this is how you can describe theorem number 1. Now let us concentrate and go to theorem number 2, right? If you want, you can take screenshot of this. So now going to theorem number 2. Again, it's De Morgan's theorem, and theorem number 2 is for any Boolean variables A and B. Now you'll realize the change. It's now complement of A or B. In the previous case, it was complement of A and B. Now it's a complement of A or B is equal to complement of A dot complement of B. So this is theorem number 2. Now let us try to prove this theorem number 2. So in this case, LHS side is nothing but describing you OR ka complement, and OR ka complement or not OR operation is described here, and not OR is nothing but NOR operation, right? So therefore LHS is nothing but NOR gate, which has got two inputs as A and B, and the output side is OR gate's output is now complemented, and therefore now you are getting complement of A plus B. So this is LHS side of this equation. Now let us see what will be RHS side. And here you can see the RHS side describing there is a dot, that means it's an AND gate, and AND gate is receiving inputs as A complement and B complement. That means the inputs A and B are given to AND gate, but before that they are complemented individually. So therefore that is bubbled must be present, that is NOT gate must be present before the AND gate. So therefore the diagram will look like this. Here you can see again the same situation. A is given as an input to this NOT gate, then output of this NOT gate will be A complement. Then B is given as an input to this NOT gate, the output will be obviously then B complement. Now you realize that this AND gate receives two inputs, A complement and B complement. Therefore, the AND gate's property is whatever input created or create or place dot between the two inputs. So the two inputs are complement of A and complement of B. The dot will be present between the two. And here the main point is bubbled word. Why? Because this NOT gate is present before AND gate. Right? So this is AND gate. Right? So the placement of NOT gate is before AND gate, therefore, and in both cases, that is all inputs of this AND gate are passing through this NOT gate. Therefore, this is called as bubbled AND gate. This is a representation of the diagram which I have shown in the RHS side. These two bubbles representing that NOT gate is present, so this input will be negated and then given to AND gate. This is a bubbled AND gate representation. So remember this bubbled OR gate in the previous case, bubbled AND gate in the this De Morgan's law, second law. The truth table can be used to verify this particular law. The truth table says that in the statement it's a complement of A or B is equal to complement of A dot complement of B, that is complement of A and complement of B. So let us verify this by truth table. Again there are 4 inputs, so therefore the 4 inputs I have already shown to you how to write down those 4 variable or different unique inputs. So there will be 0 0 1 1 and this will be 0 1 0 1, right? So these 4 unique inputs has been provided to which gate? OR gate. Why OR gate? Because this is A plus B and it is then complemented, right? Complement of both A plus B ka operation ka complement. So therefore we need to find first A plus B or A or B. A or B says that all inputs will be high if at least one input is high. So therefore first will be obviously this will be 0 and then all inputs will be 1, right? So this will be output of OR gate. Now this output of OR gate will be bubbled, right? That means it will be complemented. So 0 will be complemented as 1 and all other will be complemented as 0. And now this situation or this is the truth table logic for LHS side. Now let us focus to the RHS side. In RHS side there is a A complement and then there is a B complement. So all inputs at A will be complemented. So A complement is equal to 1 1 0 0 and B complement will be 1 0 1 0. So these are the 4 unique combinations created which are given to AND gate, right? Now AND gate's logic says that if all inputs are high, then only output is high. So here you can see these 2 inputs are high, so the output will be 1. But in all other cases, at least 1 0 is present. So therefore, the other cases is going to show you output as 0. Now, LHS truth table and RHS column, both columns are same. Therefore, you can say that the De Morgan's second theorem is verified. The theorem says that complement of A or B is equal to complement of A and complement of B. So here you can realize that complement when it is created or when it is applied on plus sign, it will be replaced by dot, right? So this is second law's proof. So in summary, we can easily verify the De Morgan's laws. The first law says that complement of A dot B is equal to complement of A plus complement of B. Diagrammatically, we have written down as it is nothing but NAND gate, bubbled OR gate. NAND gate is equivalent to bubbled OR gate, or you can see the diagrams also. This is NAND gates diagram, right? And this is bubbled OR gates diagram. These two diagrams are equivalent. These two diagrams equivalent means both are going to create same output. Therefore, they are called as equivalent. So this is first law. Complement of AND is equal to complement of, right, complement of OR of individual inputs. And the second law says that complement of OR is equal to or equivalent to complement of A or that is and complement of B, which is nothing but NOR gate equivalent to bubbled NAND gate. Sorry, bubbled AND gate. Sorry, there is a printing mistake, right? This should not be present, right? This will be bubbled AND gate, not NAND gate, right? So therefore, the diagrammatic representation will be like this. This is NOR gates diagram, and this is AND gate, which is whose complement inputs are complemented. So therefore, this is bubbled AND gate, right? So this is in summary De Morgan's theorem. We are going to use these De Morgan's theorems outputs and these two theorems continuously throughout our syllabus of digital electronics. So therefore, you must carefully understand these two concepts properly and then try to solve it yourself, so that we will be use it again and again and again throughout the syllabus. Okay, thank you.